Hello everyone and welcome to this new video where I will share with you what I learned regarding positional encoding. So today we're going to tackle one of the most elegant and critical components of the transformer architecture, which is positional encoding. In this video we're just going to see the theory, and in next videos we will see the math and the coding part. So if you look at this visual at the left, this one, you can see like the bag of words. This represents how a computer naturally sees text as a jumbled collection of data points without any inherent order. So the goal today is to move to the right side, taking this chaos and imposing a strict, meaningful sequence so the model can understand that the cat 8 is very different from 8 cat D. We're going to explore exactly how transformers understand sequence without using recurrent loops like the ones found in the RNNs. So, to understand the solution, we first must understand the problem. I call this the transformers blind spot. Look at the two sequences of the screen. No, it is good, and it is no good. To a human, the semantic difference is critical because they mean opposite things. However, the transformer processes data in parallel. It takes the entire sequence at once to be fast. Because of this parallel processing, the model suffers from permutation invariance. If we don't intervene, the model sees the exact same set of words for both sequences. So one no and one it and one good, as the scatter plot shows. The geometric representation of these two sequences is identical in the model's eye. Without encoding position, the model physically cannot tell these two sentences apart. So we need to attach a tag or an index to every word to indicate its position. But we can't just use any number. Through research, we've identified 4 critical criteria valid for an indexing system. It must be unique. So every position must have a distinct representation. Position 5 cannot look like position 6, for example. And it should be deterministic. The code must be stable. If I ask the code for position 5 today, it should be the same as tomorrow, so there is no randomness. And also it should be bounded, so the values need to stay within a stable range, for example -1 and 1 and +1. If values get too large, then they can destabilize the neural network. Also, extrapolatable. So this is crucial. If we train the model on sentences that are 50 words long, it should still work if we give it a sentence that is 55 words long during the inference. So we will see why naive numbering fails. Like you might be thinking, why not give them why not number the words like 1, 2, 3, 4, etc. Or why we don't use fractions like 0, 0, 0, 1, 0, 0, 2, 0, 0, 3. So let's look why these fail. If we try using integers 1, 2, 3, etc., the problem here would be the gradient explosion. As you get to position 100 or 1000 or 1 million, the values become very massive. These huge numbers dominate the word embeddings, effectively washing out the meaning of the word. So on the second try or attempt, if we use fractions from 0 to 1, Uh, you might say like let's represent the start with 0 and the end with 1. So the problem here is we have inconsistent step size in a short sentence. The steps between words might be 0, 5. In a long sentence, the step is 0, 1. This confuses the model because the distance between the words keeps changing depending on the sentence length. So we need the system that is both bounded and consistent. So this is the solution. We do not just append a single number to the word. Instead, we generate a whole vector, which is a list of numbers, specifically for that position. We then add this positional vector directly to the word embedding. If you look at the graph, imagine like the black vector is the word queen, the blue vector is the position 1. If we add them, we get this yellow dashed vector. We're essentially nudging the word queen slightly in the specific direction that represents queen at position 1. This allows the model to retain the word's meaning while embedding its location directly into the numbers. So the input should be the embedding of the word plus the positional vector. Now let's see the mechanism. How do we generate these vectors? We're talking about these vectors, positional vectors. How do we generate them? We use the sines and cosines waves. The formula you see here on the left. It might look complicated, but the concept is very simple. We use alternating sine and cosine functions. For even numbers, we use the sine. For odd numbers, we use the cosine. Why we use the waves? Because as we can see, they are perfectly bounded between -1 and 1, and they are smooth because they are continuous functions. They are defined for infinite positions, so you don't have a limit, which solves the problem. But a single wave would repeat itself. So how can we ensure that they are unique? We used multiple waves at different frequencies. Let's look how. So to understand the multiple waves, how they can create unique IDs, imagine a multi-handed clock. For a standard clock has a second hand, a minute hand, and the hour hand. So you have the seconds, minutes, and hours. The second one moves very fast. This represents our high frequency dimensions because it vibrates quickly. The hour hand moves very slow. This represents our low frequency dimensions. At any specific moment in time, if you freeze the clock, the combination of the angles of all hands is unique. That set of angles is your timestamp. In a transformer, we effectively use 512 different hands moving at different speeds to create a unique timestamp for every word. If this slide was confusing, we can see another analogy. This is analogy for the binary code. Look at the top row. When we count in binary 0, 0, 0, 1, 1, 0, etc., etc., the last bit flips constantly. So from 0, 1, 0, 1. The next bit flips slower, so 0, 0, 1, 1. This is positional encoding, so we can say it's just continuous version of this binary counter. Instead of flipping between 0 and 1, we oscillate smoothly between -1 and 1. The high frequency waves corresponds to the least significant bit flipping rapidly. The low frequency waves correspond to the most significant bit changing slowly. This ensures that even if two positions are very close, the high frequency waves will look different, allowing the model to distinguish them. So mathematically, we achieve this by stretching the wavelengths in a geometric progression. So this one, the first one, is has very short wavelength. As we can see, it wiggles constantly. The bottom wave has a massive wavelength. So you might ask why this is the maximum. It is a tuning parameter chosen to be large enough so that the slowest wave, this one, doesn't complete a full cycle for any realistic sentence length. This prevents collisions where position 1 and position 1000 get the same code. If the wave doesn't repeat, the code remains unique. And that's what we're trying to achieve, basically. This brings us to the very famous visualization found in the transformer paper, the positional encoding matrix. Here, the y-axis is the position in this sequence, let's say from 0 to 100, and the x-axis is the embedding dimension, 0 to 512. On the left, you see chaotic high-frequency pattern. That is the second hand. It's spinning fast. It captures fine grained details. On the right, you can see it becomes smoother, changing like the bands of color. That is the hour band in our clock. It captures the global position, telling the model generally where it is in the sentence. Together, this gradient provides the model with a unique fingerprint for every single token. So now this is a killer feature. It's not just about unique IDs, it's about relationship. Because of the properties of sine and cosine, we can mathematically prove that the encoding for position k is just a linear rotation of the encoding for position. So why does this matter? It makes it incredibly easy for the model's attention mechanism to learn relative distances. If the model wants to attend the word 3 steps back, it just needs to learn a simple rotation matrix. It doesn't need to memorize every position index. It just learns the function of moving back 3 steps, for example. So it's not a memorization problem. So if we want to generalize it to long sequences, so because earlier we mentioned that we have a problem of long sequences here, here. This slide shows us why the sinusoidal functions are superior to the learned embeddings for this task. Imagine if we trained a model only on sentences up to length like 50. This is training up to 50. If we suddenly give it a sentence of length 500 during the inference, if the model just learned position IDs, it would fail because it has like never seen anything that's greater than 50. But because our method uses mathematical function, the curve, the pattern naturally extends forever. The model understands the concept of wave, so it can calculate the code for position like 500 even if it didn't see it during the training. So let's put it all back together. In the pipeline, we take a token, for example the cat. We look up its word embedding, the semantic meaning. Simultaneously, we calculate the position vector using our sine cosine formulas, and then we add them together. This combined vector now enters the self-attention layer. The transformer now knows what the word is, cat, and its position. So if we say the cat, it knows that cat has position 2. So we have successfully imposed the order. Now we have seen the why and the conceptual how. We understand the need for vectors, the power of frequencies, and the elegance of rotation property. So in the next videos we will see the exact mathematical part, and then we will see the coding part using an example in PyTorch.